Dear guests, welcome to our work. We very enjoy to see you here because we started this activities not so long time ago. So 1 year before it was empty rooms, nothing. Now there is some laboratory. Mainly it's devoted to this development of cold direction bolometers and application for, first of all, boomerang project. Then we are thinking about millimetron project. And also Celia, we remember your invitation to take part in Olympia if we are ready.
Yes, it's still the same invitation.
Yeah.
Even more.
Yeah. We are discussing now, maybe we continue to discuss, of course, our main goal for boomerang, but if there is this opportunity,
Yes.
we can develop quickly some system, smaller scale, to test it, this flight, and then for boomerang it will be well developed and tested system. And by the way, when do you think now will be launched?
As you know, it depends also from
Yeah.
a bit of day, which is more political than
Of course, yeah.
the overflight permission. But we went one step ahead now, because the Italian Space Agency, meanwhile, gave us the possibility of taking care of the launch itself with whatever organization we wanted, cheap. And so they gave us also the equipment that they use for ballooning, just to launch Olympus. So basically the materials which are in Svalbard are under our control now. So the only thing we miss now is the overflight permission. And they gave us the 2 balloons, so they purchased the 2 balloons. We have one for launching and the other one is a spare. This balloon is 800,000 cubic meter balloon, because the equipment overall weight is about 1,850 kilos, so it's not a small payload. So you need also a spare balloon. So we have 4 balloons. One is already on site, the other one is in Trapani.
Yes.
The equipment for launching is there. And from their point of view, they want this thing in the stratosphere next year.
Next year. So that means, I remember it was June, suppose.
It was June, but I don't think that the overflight permission will not come to us this June. It says always 6 months are needed for the authorities, the Russian authorities. If there was a overflight permission, I was shipping everything on the 2nd of April, let's say, not the 1st, the 2nd of April.
And already detectors.
The detectors we are testing the TES now.
Yes.
Finally in the final configuration in the cryostat. And we tested with cool down with also the new high frequency arrays, which are bolometers, and these days they are testing, starting today probably, they are testing with the optical source.
How many TS?
It is, what is open, 22, no,
22.
23.
I mean 22 each
The pixel.
22 pixels.
Pixel.
Yeah.
There is also one blind, but it's okay. So it's 22 sensitive to photons.
Yeah. Do you have other type of bolometers also?
The other ones are, come si chiamano? Sono bolometri with a standard readout with
These are
FET.
the high frequency bolometers are high resistance bolometers with it was niobium. It's an alloy, niobium silicon.
Silicon niobium. They are drilled by Grenoble.
Oh, yeah.
You know this.
Camus. Benoit.
No, ma il tizio che li fa a Parigi non si chiama fa i film. Louis Dumoulin. He makes the films.
Yeah. Is it laboratory of...
He's in Paris.
In Paris? Ah.
Yes, Dumoulin makes the films in
Camus,
Paris, and
no.
then they assemble in the detector in Grenoble.
Is it laboratory of Benoit in Grenoble?
Yes.
Yes. Yeah, of course. Good.
They are. We had a very strange
How many of
experience.
this silicon niobium?
They are two arrays of 23 each. And we had a bad experience after the fourth cycle of the fridge. We saw a very strange behavior in the detectors, and finally we figured out it was the load resistors, which actually are in principle very high quality. They choose the same one I would have chosen for. So the cold stage load resistors started breaking the body of the resistor. So we are in the process of changing them.
Yeah.
We finally got the model we used for the first flight of Boomerang.
And what readout do you use for this?
It's FET,
FET?
FET, sì.
FET?
FET box,
JFET or?
JFET,
Self-made.
assembled, self-made.
Is it cold?
It's cold.
Sì. 120 Kelvin heated up
Yeah.
to minimize the noise.
Yeah. No, it was typical for you before to use this system.
Yes.
Is it your readout or they produced?
No, the cold
we made
readout, yes, we
Yeah.
made, but the load resistor instead is mounted in the same part where the chip is, and is in the board, so they did that. Also, we had trouble in assembling because we sent the drawing of what we had as a space, but the space was not respected by the builder of the board. So we had to change many parts inside. Was a very hard job to make the arrays fit inside.
Yeah.
And the other thing which took a lot of time was a shielding instead of the TES. Finally, we managed to make a shield.
But is it
Which
due to
is-
squids or?
Yes, squids. See,
Yeah, I mean shielding.
Series arrays.
Shielding is needed due to squids, yes?
Squids were from NIST.
Yeah.
From NIST, the first two modules we purchased, very expensive.
Yeah.
Then I hired an Italian who was for a while in Vancouver collaborating with people at NIST.
Yeah.
So he mentioned that these squids were very expensive. So the guy said, okay, what's wrong with starting a collaboration? So the next two he gave for free. We started the collaboration. Basically, squids at NIST they are off the shelf now. So
Yeah, no, okay.
for them is they produce for everyone, for many,
Italian.
for many. No,
Everywhere.
for people in Canada, for people blast people used them. No.
Yeah, but many experiments.
Yeah.
Anyway, if we might find a space in the focal plane to add
Yes,
CB.
yes. I think
Yes,
that.
and What,
No,
is,
we think-
what is
yeah.
frequency and
350.
350, yes?
350.
I mean, one array is 350, the other one is 450.
It's too high frequency and too low frequency.
You mean we could do both 350 and 450, yes? Or
Well, right now we have these bolometers
two lines?
for both
Yeah, but
arrays.
there are
There are
wiring which we can use. I mean, we
to
have
add the pixels, yes.
because in the original plan you always plan to have some wiring which is spare just if something bad happens.
Yes.
And up to now all the lines work, so we have the spare cabling
Yes.
all cabled, so we can add.
But how many lines do you have now?
We can
Additional,
add
you mean,
additional.
two or three.
see.
2 or 3 detectors, I mean,
Ah.
2 or 3, 4
So if we
wireless
want,
lines.
if we want to add one detector on one side and one detector on the other side, there is place,
Uh-huh.
and we still have two spares.
Okay, is
Actually,
this-
4 spares.
Four? Yeah.
I mean, 4 wires are needed for one detector. So
How many wires do you need?
It's a good question. In principle, we are using 4-point measurement scheme.
okay.
4-point measurement scheme. But if you like to save some wires, for current bias we can use only 2 wires and then several bias resistors, hold resistors.
Ah.
But for voltage, of course, separate. But about wires, how many wires do you have? Yeah.
8
Liberi,
liberi.
Huh?
Sì. I need to check better,
We need
but
to
I
check
think
because these are from the pixels which have not been active in the arrays.
Yes.
Okay, so I don't remember if are 1 each or 2 in one and 1 in the other one. That's
Okay.
what we have.
No, I would say that optimal number would be if you place 2 detectors.
yes.
Yes.
And test them, and
Yes.
it's better than 1. And but no.
Yes.
Which
enough.
is,
Better statistics.
the frequency range where these detectors can work in your
No,
detector?
now we design for 350 Hz, but in principle
Yes.
we can do any if you like.
But you have to change the design from 350 to 450?
Yes, no problem.
But the same design cannot work on both.
By design can work on both.
No, I mean the same actual device.
Ah.
If you produce for 350,
The same actual device.
how
It's-
does it degrade at 450?
It's a good question.
Similar device.
Stanislav, it's a question that we discussed just today intensively. They asked, could our device use for both frequencies, 350 and 450? And you can show depends on frequency, and so this array, it's quite insensitive to frequency, not selective frequency. You can use for both.
Did you try to make a spectrum? I mean,
At least yes, there is some simulation for
in the
this, to
simulation.
the
No,
array.
I mean on actual devices. Did you try to make
In principle, yes. In principle, yes, but there are 2 options. One option to do the spectrum using BWO, that is so that we saw there, we can do it. But for noise measurement, we usually use simply thermal source and
Okay.
some filters to select bandwidth.
I see.
In this experiment, we can do, for example, we can select first bandwidth, then we can change filters, test another bandwidth, then test the system. I can guess it's quite insensitive to frequency, and you will see now, and especially if we have these 200 micrometers step, it will be just convenient couples. Okay, how will we work? And
I
what
can.
is suggestions? We will do some presentation
Yes.
now, different topics. Then possibly we don't have enough time for all discussion. Tomorrow we will do both presentations for Olympia and Boomerang. Then we return back here and we'll have joint discussion about all
Okay.
sharp questions.
Sure.
Okay.
Sure.
So we can start from input, from quasi optics. Stanislav
Okay.
started about his simulations. So Stanislav.
Sì, sì, no, dopo.
Professor,
see is the same solution we have.
Looks very similar, but I mean it can be the same surface. I can call now and just ask if they supplied something to Rome University.
I'm not sure. I have it in the lab.
And so there are some problems with what? With power is lower.
The current
The
is
current is half of what,
what is nominal.
and the intensity goes down,
Fluctuates
but goes down
by
slowly.
100%.
But
It's a big change. So if they have suggestions, what to do?
Okay.
We have some questions from work of Boomerang. In this picture we saw the model of Boomerang telescope,
Yes.
and model in program Zemax, three mirrors and the focal plane,
Yes.
and the initial construction of Boomerang. Model the dot source generate the plane wave. Plane wave mirror from the first mirror, second, third, and it's generate the stain in focal plane. The
Yes.
diameter is around 4 millimeters.
Yes.
We can set the lens before focal plane. What the focal stain without lens, around 4 millimeters, and the focal stain with lens around 1 millimeter. We work at the diffraction limit for these optical systems. The scale 5 millimeters in left picture, and in the right picture 1 millimeter. Another view on this problem. We can calculate from theoretical formulation this stain, or we can work from ray tracing. In the same scale, on the left in the area, and on right picture on this zenith zone. We can calculate the electromagnetic waves from program AGLM Pro. Also. And we obtain the same results. Similar same results with ray tracing. Can compare the calculation models and the theoretical models. Well, we have some questions about what wave fall down on the mirror. What, if we use lens, we can obtain very small angle, or in small angle, and with lens
But it was formulated that angle is 90 degrees.
90 degrees, but with this we have 5 degrees or less from lens. If lens in the focal plane.
So this is the lens on the focal plane, okay? You're speaking about the lens in the focal plane that you added, okay?
This picture show what we can see in field intensity on array matrix of SEPs. Where background wave pull down on mirrors, and in matrix of cell we can see similar picture.
Yes. This is the array of detectors in the focal plane.
Yes.
Okay.
So I can see that the full matrix with lens have a very small angle for radiation mirror.
Yes.
The matrix of SEPs have the same angle as mirror.
Mirror.
Mirror. It's the same angle, with 19 degrees or enough degrees. Is
That means
automatically
yes. But maybe I will switch to this
switch with degrees.
А?
Ну, вот переведите точнее. Вот первый вопрос. Линза выдает очень узкий луч, который может не облучать все зеркало. Очень узкий, под малым
Ну,
углом.
это вы уже сказали.
Да. Либо мы ее должны расфокусировать, и тогда она бесполезна.
Ну, такая, может быть, мы
Да.
этим матрицами передвинемся.
Вот, если про линзу говорить. Либо
No, statement was
вопрос
question
о
was,
матрице.
question was that lens can create very narrow end for matching. But if we use array, 2D array, in this case, this angle could be as we like or as we need. So for matching, let's say this 90 degrees, as Stanislav stated, it should be automatically tuned to this diagram. So, no, and I don't know, in this case, or we should tune lens, but lens is quite complicated system. I would say that we are now making more of these 2D arrays with more opportunity, with some useful properties, with better resolution for polarization. And I would suggest to switch to that topic.
So let me say if I have understood. Using the array for each pixel,
Yes.
you fill the 4 mm original spot.
Yes.
Okay. So you don't need the lens.
No.
This is the idea.
Yes, this is the
Did
idea.
I understand well? Yes,
Yes.
I think it's a good idea to avoid the lens because
Of course, yeah.
it's complex to make mechanically, and you should put it very close to the array, and
To
it's
match, and
complex.
also you find out that in both original work of Zmuizinus lab and also in Stanislav work,
Yes.
there should be very good alignment.
Yes.
If we
Yes.
have misalignment lambda by 4, it already will see another pattern, it will be very bad cross polarization.
Uh-huh.
So in any relation, this array looks very no, more preferable.
Yeah, I agree.
Yeah,
I agree.
okay.
Yes.
Let's switch to
Какое разрешение мы хотим получить, требуемое? Ну,
О.
вот 4 миллиметра, ну, по углу. То есть 4 миллиметра пятно соответствует размеру ячейки.
Да.
Внутри ячейки, то есть вот насколько неоднородно поле может быть.
Да, наверное, не насколько. это
Какую-
просто
ну,
так целое.
Оно уже, нет, ну оно здесь уже неоднородно, вот 4 миллиметра.
Ну,
Ну, здесь
всё
вот
равно
интенсивность в середине единица, здесь по краям 0,5.
Нет, я больше не то,
Или
что
это вот
теперь.
не так существенно, что ячейка как один пиксель
Конечно,
рассматривается, и тогда мы можем считать, что она относительно размазана
да.
за счет аппаратной функции.
The question was that if we use this array, we have more or less uniform field for this area, 4 by 4 millimeters.
Yes.
Yes, and then we can measure as whole this power
Yes.
and compare from pixel to pixel.
Yes.
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 So the beam will have its shape,
Mhm.
okay, which is not a Gaussian probably. It will be more square as a profile,
Yeah.
but that's fine. We
Yeah.
like it. No problem.
Another question, what compromise between absorber power and cross polarization?
Yes, we started to speak about this
Yes,
in the other room.
Our speaker.
So maybe I can try to explain better what we do, and then we decide.
Mhm.
Okay.
Okay.
And the general problem is to measure a small polarized signal embedded in a large unpolarized signal. Okay, because we have 2.7 Kelvin from the cosmic microwave background, which is not polarized, and the polarized fraction is only, say, 3 microkelvin. Okay, so it's
Kelvin, it's quite.
it's very small. Okay.
Yes, small.
Okay. So now, if you want to measure these 3 microkelvins using 2 detectors sensitive to the 2 orthogonal polarizations, okay,
Mhm.
you have to do this difference, okay, and the common mode, which is 1 million times larger,
Yes.
has to be rejected. Okay, this is the main problem.
Yes.
And rejecting 1 million times larger common mode is very difficult.
Mhm.
So this is why we introduced a polarization modulator. Okay, because using a rotating halfway plate in front of a single polarized detector,
Mhm.
okay, you modulate the incoming signal, and you see a small 3 microkelvin waveform, sine wave, on top of a 3 Kelvin offset. Okay,
Mhm.
you can separate the offset because it's
Yes.
DC term. Okay, and you only see the modulated signal.
Mhm.
If you use the same rotating halfway plate in front of 2 crossed detectors, you will just double the sensitivity because you will see 2 sine waves shifted by 90 degrees,
Mhm.
okay, on the 2 detectors. And that's fine. I mean, gaining a factor 2 of sensitivity is important also that, okay? Now, which are the problems? First of all, the halfway plate is not perfect.
No.
It's not at all perfect. So the modulation is not 100%. Maybe it's from 10% to 90% or something like that.
Mhm.
Second is a mechanical system which has to work cryogenically without dissipating power on the helium reservoir and so on. So it's a big problem because, for example, my friend Shaul Lahanani made a levitating halfway plate which rotates on a superconducting magnet. Okay, so it just rotates without much dissipation, but there is dissipation because there are eddy currents in the ring, there are a lot of problems, so
course, yeah.
it's not as easy as it seems.
I
You have
agree.
to start the motion, you have to, and the motion will slowly
Mhm.
slow down,
Yes.
and after maybe 1 hour we have to give another kick and start again. So, and when you move the system, the wave plate starts to librate, you know, and so on. So it's not very easy.
No.
But anyway, they made it and has been tested even in flight. So they are quite advanced on this. And they modulate at a frequency of a few hertz, okay, continuous modulation, which you understand is very good, a few hertz, because means that you compare the two polarizations with a frequency of a few hertz, which is quite good. Okay,
No, but frequency is quite low.
eh?
Frequency is quite low.
It's still low, but
Yeah, because
it's
for
better
one
than
upon
DC.
F noise it would be, of course,
Yes, but it's
not-
better than DC. Okay.
is of course it's better than DC.
Yeah.
But immediate idea.
Yes.
What if we use these two component to amplifier and switch from one to another? It will be
No,
exactly
of
the
course,
same.
that will help with the instability of the amplifiers, but will not help with the instability of the detector. Right?
No instability of detector, but we can cut off, practically speaking, this 2.7 Kelvin in this case, because we will compare between them or difference between them. So in this case,
To the accuracy, you can do it. I mean, the problem is that the common mode is 1 million times larger than the small signal.
common mode, yes, common mode is
Is,
larger.
Is very large. So that's the main problem is right there. Huge
No, I
common
mean
mode.
if you subtract from one to another,
Yes.
it's the same as modulation of this halfway pipe.
Yes, it's the same. It's the same, but any drift
Of course.
will enter the result.
If it's separate drift in
In the
each
two
detector,
detectors, yes,
it
this
will
is what
be
I'm saying.
And in
Yes.
this case, I would say that why drift? If you have this large scale array and they cross each other on the same
Yes,
place,
but maybe imagine that the temperature of the refrigerator drifts. I
but
mean,
it's for both.
For both.
They exactly,
for both,
They
yes.
contact, they cross each other.
Yes, but
Yeah.
are they matched so well that I mean the dependence of each of the detectors on the temperature of the refrigerator is exactly the same,
I think so.
to 1 part per million.
They cover whole area.
To 1 part per million. That's the main problem, right?
This can be measured.
Yes,
There will be
yes.
already
I mean,
in
we
the
need a
can measure
measurement
and
of
test.
this.
I hope so, because they feel large area.
Yes.
And just in the same position. They always in contact, in thermal contact.
So to give you a feeling of this, we did this measurement with the Boomerang in 2003.
Yeah.
Okay, and we used 2 bolometers, crossed
Yeah.
bolometers, with the separate amplifiers. So exactly, And we were able to detect CMB polarization at a level of a few microkelvin, so it's not impossible. Here would be much better, of course,
They
right?
cross each
They are
other
in the
exactly
same
the same.
chip, they are
Yeah.
so close each other. So,
And
to my
then-
point of view, is a very interesting opportunity.
Yeah.
What you tell me,
Yeah,
but
you
I
know-
want you to be aware of the problem.
Yeah,
Okay.
and you know, one more speculation, philosophical speculation. When I started with bolometers, of course I expected some one open of noise and so on. But when we go to array, it looks it should be proved. And my good example in my mind is germanium bolometers. Semiconductor bolometers, in principle, each piece of this bolometer is quite noisy. But in general, in big volume, they are very good.
Because it's
in
large.
1 upon F noise, yes, less than 0.1 hertz.
Yes.
I am expecting something here. And if we move to larger scale, all properties will be improved.
Yes.
And let's hope that we can overcome this problem.
Yes.
Of course, in compare with your previous realization when it was two different detectors, it could be considerably better.
No, I'm sure it will be much better. Now, is a quantitative answer that we need, right? Qualitatively, I agree, it will be much better. Now, how much?
How much? Okay, let's continue to discuss and listen to this question. Okay, continue.
In this picture we can see calculation results for large matrix. The absorbed power divided on pull down power in active region and the cross polarization. Question: what bandwidth we need from to
Let me see.
megahertz?
I tell you from the working at balloon altitude, we have to stay away from the atmospheric emission lattice. Okay, so the filter can match the atmospheric window at balloon altitude. And now I can we can copy the
one of Oli?
no the one of Boomerang we had in the first flight, which was wider than Olimpo.
That was wider. That was centered at 410 gigahertz.
No. 345. Sì. It takes a few seconds.
Ti puoi lavorare a una sola frequenza. Su questo.
Una banda alla volta, no? I have another question. Are you able to make also the 150? I mean,
Yes.
150 gigahertz.
Yes.
Because it would be great to have both
Of
sets
course,
at
we
this
discussed
point.
with you
Yes.
when I visited you. You said you have now from GPL maybe 9 old balloon. But if we manage to do better, we can do it. Yes, we can. Yes, no problem. Because our balloon is not sensitive to frequency. It's only a question of antenna side and
Yes.
should increase
Yes.
proportionally. Yes.
Il 50 in realtà è 340, mi sa.
Sì.
340 mo. Erano quelli laterali. No.
I get answers for my questions.
I'm sorry. It takes a few
Not yet answers, but
I
there are only questions yet.
to open this file. And I can show you if you want.
C'è il lavoro. Questo però è quello del 2003.
Non importa, il filtro era utilizzato per la
90. Поверьте, 12.
Se vuoi farlo vedere deve
Главное, есть ли у нас еще какие-то вопросы к входной части? Что мы в прошлый раз обсуждали? Окей? Пока по входной.
То есть тут уже чувствительность определяется и как бы кросс поляризации и прочее.
Ну да, но почему там тем больше, тем лучше.
Да-да-да, потому что кривые эффекты дальше. Они как бы
Да, да, вот они как раз выбирают.
Хвост-то длинный, может быть, его подтянуть.
Да, можешь, кстати.
Okay, so these are the bands with
That is quite long.
okay, okay.
But bandpace is defined by filters, yeah?
Yes. So these are the
Quite.
filters we used in the stratosphere, so they are fine. Okay, and we labeled only the half-hour
Level.
points. Okay, so for the 150 gigahertz band, we go from 125 to 170. Okay, this is the low frequency band. And for the 350, we go from 290 to 410, let's say. Okay, so this would be ideal. If you can approach this good performance over those, these are the widest bands you can use. Okay? Then, if
But sorry, do you mean that we prepare bolometers for each bandwidth or the same bolometer with different filters?
same bolometer with
See.
different filters is fine. I mean, the band is defined by the
Они
filter.
rather close, it's the same, certainly. Is it Planck, yeah?
Sorry?
Planck?
Dashed line.
Yes, is
Yes.
the derivative of the Planck function, I think.
For 2.7, yeah?
Yes. It's 2.7 Kelvin, you take the derivative
yeah.
because we have a fluctuation, and that's the function.
Clear, thanks.
So, yes, so this band is mostly sensitive to CMB. This band is a monitor mostly sensitive to interstellar dust polarization, which is the other target for boomerang.
Sorry,
Yeah, but
question
this
again.
is the
Yeah,
seventh
So
flight.
anyway, what is planned to have separate system because it's separate filters. And we
Yes.
fix bolometers with proper size of antennas for each
Yes.
band.
Yes.
Эту статью Тибрил, нет?
Okay.
So we have
Есть у меня,
half of the
просто я как-то
focal
не обращал
plane,
внимания на эту
which is filled with 350 gigahertz
Yeah.
detectors and has its own filter.
Как бы она была.
Yes.
Статья я
And then
её
the other
видел.
half
Mhm.
is filled with 150 gigahertz detectors, and that's
Yeah. How many of them would you like to have? 150.
so. If you look at the focal plane.
Yes.
There
Therefore.
Yes, but we cannot fit
No,
the
no.
size of the
Size of
focal
course,
plane
yeah, yeah.
is,
Кстати,
Ну, just
is
question.
the same
Знакомые
size,
цвета,
is
нет?
the same physical size of the 350.
Yes.
But you fill with 150. So
Yeah.
each detector is 3 times one. Have 9 times less detectors.
Okay, but
So
anyway,
you get
before it
10
was 8
detectors.
or 9.
9, 10,
No.
depending on how you pack the detectors. But it's the same size of the other focal plane.
Yeah, no. I remember your focal plane, yes.
Yes.
Okay. It's good.
Would be wonderful to have the same kind of detectors, the same
course.
electronics. I mean,
Yeah,
so-
the same electron, same system, so.
Yes.
And also our idea to fabricate all pixels on the same silicon wave of 2 inches.
Uh-huh.
Yeah, in this case it will be even more convenient to use.
Yes.
Yeah.
Yes.
So, whole array, no any additional,
Нет.
There is already some design. Now, действительно, статус
Yes.